the oxidation reactions. Oxidation reactions. So yesterday we had a discussion about the reduction reaction, and now we will see the oxidation reaction of the different functional groups. So this is what myself and my group is working on, that is the organic synthesis of the compounds, nanocatalysis and CH activations, nanocomposites. Nanocomposites are having around not around 6 patents we have filed. uh, One is about to approve. Then material science, synthetic high performance polymers, biodegradable polymers, in which we are preparing the nano vehicles, nano medical vehicles, and of course the green chemistry and heterocyclic chemistry. So this is the syllabus so far we are going to see. That is the introduction and oxidation of hydrocarbons, alkanes, alkenes, aromatic ring, phenol, alcohol, diols, ketones, in that aldehydes and carboxylic acids and their derivatives, amine and hydrazine and sulfide. So these many functional groups are included for the discussion of the reduction of the reactions. Well, so first of all, we have mentioned yesterday that what is the oxidation. So in oxidation, we have said that it can be addition of oxygen or removal of hydrogen or removal of electron or increasing oxidation number or addition of the electronegative elements. So this was given definition for the oxidation. But an opposite to that, that is the reduction. So here also the oxidation mainly can be carried out by the removal of the electron. Then the second one, that is the by removal of the hydrogen atom and by transfer of the removal of the hydride ion and addition of the oxygen. So these are the mainly three major definitions. Fourth one, that is the addition of oxygen. These four major definitions are we will discuss it in the oxidation. So before we start for the oxidation, we could say that there are different level of the oxidation. So all the functional groups are classified into 5 oxidation levels. So what kind of levels are there, that I wanted to discuss. So that is the this is just okay level I wanted to discuss. So you can say that if any of the compound Just a minute. Okay, so any of the compound is attached to the carbon or hydrogen. Any of the compound is attached to the carbon or hydrogen. Just a minute. So this is a carbon, and this can be any of the carbon or hydrogen, let's say. So this center carbon atom is not attached to any of the negative, any of the negative element or negative atom like oxygen or nitrogen or sulfur. So in that case, it can be known as zero level oxidation state, because this carbon is not attached to any of the electronegative atom. Okay, and this is the lowest oxidation state for the carbon, that is zero, because it is not attached to any of the electronegative atom. So you can say, if suppose it is CH3, 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 let's say CH3, okay, CH3. Then here also, what is the degree? Degree can be oxidation level is zero, because none of the electronegative atom is present here, and that is not attached to the carbon atom. Okay, now you can just look at this example: CH3, CH2, and OH, let's say ethanol. So now, can you able to say that what is the degree of this carbon atom? What is the oxidation state of this carbon atom?
Primary.
Primary. So it is level 1. It is level 1 because one functional group, this is the functional group that is attached to the carbon atom. This is the only carbon. Okay, but this is the electronegative atom and functional group is present. So that is why it is the level 1. In zero level, none of the functional group is present. Whereas in the level 1, one OH group is present. Now, will you able to say what is about the oxidation level of this carbon atom? It is the thiol. What do you say?
Primary.
Yes, it is level 1. Okay, here it is. This is the chlorine. So what do you say about this carbon atom? Again, it is a level 1. Okay, so in all the cases, we have said that this is the level 1 oxidation state. Now in place of this, I am mentioning this. Okay, now what is the oxidation level of this carbon atom?
Level 2.
Level 2, because two methoxy groups are attached to the central carbon atom. So it is a level 2. Okay, and if there is a 3 functional group attached to this, suppose here I am putting COH. Okay, here I can say COH. This is H. Now what do you say about this? It is the level 3, because this is the functional group. Okay, this is the functional group that is attached. Then one more functional group. This is the another functional group. Only one hydrogen atom is there. So we can say that it is a level 3. Now level 4. So just you can recall the structure of the, to this pen. This is the carbon tetrachloride. Now what do you say about this carbon atom? It is level
Level 4.
4, correct. Okay, level 4. So level 0 you have seen here. This is the level 0 and it reaches up to level 4. So this is the basic of the oxidation level in with the carbon atom. Now oxidation of the hydrocarbons, in which oxidation of alkene, that is the hydrocarbons, are to be discussed. So basically the reactions of the alkenes are carried out, or it can be classified in 2 general groups. So oxidation of the pi bond without cleavage of the sigma bond, without cleavage of the sigma bond. Okay, oxidation of the pi bond. So oxidation of pi bond, double bond, because it is a alkene. So alkene is there, so double bond is involved. So oxidation of pi bond, but without cleavage of the sigma bond. So this is the pi bond and this is the sigma bond. So without cleavage of the sigma bond. That is the known as the oxidation without cleavage. Whereas the another type is the oxidation of pi bond is taking place, but with the cleavage of the pi bond, cleavage of the pi bond. So this pi bond is also getting cleavaged. So in that case, we could say that the oxidation is known as the oxidation cleavage with oxidation is cleavaged, or oxidation cleavage. So this could be considered. So without cleavage of the pi bond, without cleavage of the sigma bond, and with the cleavage of the sigma bond. These 2 types are there. So now we are looking at the oxidation of the alkenes. So this is the oxidation of the alkene without cleavage of the sigma bond, without cleavage of the sigma bond. So this is a alkene, correct? Now in that it is a pi bond and here it is the sigma bond. So nascent oxygen, this is the nascent oxygen, it is mentioned in the bracket. So basically this nascent oxygen can be generated from the peroxides, okay, from the peroxides, so that hydrogen peroxide or metachlorobenzoic acid, all these are the peroxide in which nascent oxygen, because oxygen is always exist in the form of the molecule O2. So single oxygen is taken, that is why it is known as the nascent oxygen. So here the oxidation is taking place where cleavage of the pi bond is there. In that case the epoxide is forming. So this bond is remain as it is. This is the sigma bond. So oxidation without cleavage of the sigma bond. So in this case, oxidation is the mild oxidizing agent, the nascent oxygen. So this could be carried out in the formation of the epoxide, and for the formation of the epoxide, these are the reagents. 4 reagents are utilized. So what are the oxidizing agent? O2 gas in presence of the silver, then the organic peracids, perbenzoic acid, H2A2, hydrogen peroxide, metabromobenzoic acid. So all these type of acids are also gives the oxidation and forms the epoxide. Then the tertiary butyl hydroperoxide, TBHP. Okay, this is the structure of it. So this also considered as a epoxide formation oxidizing agent. The fourth one is magnesium monoperoxythalate, MMPP. So that is also one of the oxidizing agent for the formation of the epoxide. Potassium permanganate is also considered as a oxidizing agent. Then osmium tetroxide, that is also there. So these six oxidizing agents are utilized for the formation of the epoxides. So ultimately, this is oxidizing the alkene or double bond olefinic compound. These five can be considered. So just look at here. This is the alkene. This is the alkene, and this is the per acid. This is the per acid. So just it forming the the cyclic transition state. Here in the center it is given, and later on it gives the epoxide. So here how this bond formation is taking place by cleavage of the pi bond. So that is why this pi bond is given in the dotted line, because this pi bond is going to cleavage. And so far it is utilized or acids. Okay. So in that case, this how the oxygen linkage is taking place. And in the later stage, one of the oxygen, that is the nascent oxygen, say only single oxygen comes. So in that case, this single oxygen forming the cyclic transition state, that is known as the epoxide. So all this metachloroperbenzoic acid is used where alkene gives the peroxide. Alkene gives the epoxide. Here also, the double bonds are there. Double. Okay, is it okay? Okay, is it okay? Hello, is it visible now? Urmi?
Yes, sir.
Okay, thank you. I lost the networks. So here, the double bonds are there. Okay, double bonds are there here between the carbon-carbon, and here also between the carbon-carbon in the ring. So in the cyclic alkene, the reagent approaches from the less hindered side of the double bond. In the group of that, you can see here, less hindered carbon atom can be oxidized. So in this case, it is clear that it is the less hindered because here it is a bridge, carbons are there. So it is hindrance is taking place. So in that case, the oxidation will take place from the less hindered side. But in this case, if you look at where two substituents are there, and one double bond is inside the ring. So more alkyl substituted alkenes react faster than the less substituted double bonded. So this double bond is more substituted because two methyl groups are there. So more substituted double bond is going to oxidize first, and then this bond is going to oxidize. So that is why in presence of the metachloroperbenzoic acid, oxidation is taking place and forming the epoxide. It is stereospecific. It is stereospecific, and the addition of the oxygen atom across the double bond is always syn addition. So that is why we are getting the syn product in the oxidation. Here it is the epoxidation is formed from the double bond in presence of the fluoro per carboxylic acid, and followed by the hydrolysis gives the trans diol, because hydrolysis is there. Okay, hydrolysis of the epoxide gives the acid or both the diol here in this case. Now conjugation is there. When conjugation is present in the structure, then the conjugation of the alkene double bond with other unsaturated group reduce the rate of the epoxidation because the delocalization of the pi electron ultimately. So that can be possible in the alpha beta unsaturated acid and ester and its derivative, and that is why stronger reagent is required. So this can be considered as one of the best reagent, because here it is the alpha beta unsaturated compound is there. So resonance of the pi electron is taking place. So this carbonyl group is not easily allowing to oxidize the alkene. So in that case, it is required to use oxidation of the alkene is taking place in presence of the carbonyl group. Now here it is the good example of the Baeyer-Villiger oxidation is given, and it is good for the oxidation of the aldehydes and ketones. So this is familiar to you, the Baeyer-Villiger oxidation, where the epoxy is taking place. This is the another example where epoxidation of the alpha beta unsaturated ketone is very good substrate for the preparation of the alkenyl ketone. So for that, it is required this reagent. This reagent, it is tosyl, NH2. So you can say it is the tosyl hydrazine, and it is a good leaving group. So by using this, the reaction is proceeding, that is known as the SNOSR fragmentation reaction. So in that case, this triple bond is generated. If you look at this, it is the epoxidation. So once the epoxidation is taking place, and later it is forming the triple bond, but of course here we are getting the alcohol or the ketone. This is the another oxidizing agent utilized in the presence of the vanadilyl acetyl acetonate and the molybdenum derivative of the molybdenum acetyl acetoacetate. These are also good specific uh, oxidizing agents, because if you look at the structure of it, here it is the double bond, this one is also double bond, and one more OH is also present. So in that case, you can say that this is more substituted alkene, and this double bond is less substituted. So that is why oxidation will carried out with this double bond instead of this double bond. But here the oxidizing agent is changed, that is the derivative of the molybdenum or derivative of the vanadilyl or vanadium. Now perhydroxylation. So you are familiar with the perhydroxylation for the KMnO4. So when KMnO4 is utilized, then it is utilized as a strong oxidizing agent. And KMnO4 is not primary standardized, it is utilized as a self indicator. So in acidic media, alkaline medium, and the neutral medium, so how this is generated, how this reaction can be processed. So in all the three medium, the KMnO4 can be utilized. The application will come in the later stage. So oxidation with the KMnO4 proceed through the formation of the cyclic manganese ester, and in that the product normally gives the diol. So diol is considered as a one of the products. So that is why the unsaturations can be proved by the using the KMnO4. So that is why it is known as the stereo. It is also the specific reaction because it gives the diol in that reaction. So here it is the best example of the KMnO4 is given with the alkene, where it gives the diol. So we are just observing the color change of the KMnO4 while adding to the unsaturated compound. So in that case, the violet color of the KMnO4 getting changed in brown. So that is why we are observing that the given compound can be given the unsaturated compound. Now in presence of the long chain or the carboxylic group, that is the highly electron withdrawing groups, so that is also present over there, but still it gives the good oxidizing product, that is the diol. Now this is the one of the observation that you can see that when the KMnO4 is alkaline, when KMnO4 is dissolved in the NaOH or alkaline solution is utilized, then it gives the diol. But when the KMnO4 solution is kept neutral, then it can be the aldehyde. That is the difference in the alkali medium and the neutral medium. Now another oxidizing agent is the osmium tetroxide. So osmium tetroxide is also a good oxidizing agent for the addition of the alkene to osmium tetroxide, and it forms the cyclic osmate ester, and this is the osmium tetroxide forming the complex with the pyridine utilized as a solvent, and sometime it is also utilized as a catalyst. So later the ester is hydrolyzed and sodium sulfite is forming along with the oxidizing product. So this is the mechanism of the compound, this is the alkene, but here it is the osmium tetroxide is utilized, in which osmate ester is forming as an intermediate, and finally it gives the diol. This is the another mechanism. Now osmium tetroxide is highly toxic and also the expensive. It is very good oxidizing agent, but this is the drawback of the osmium tetroxide. But it is valuable reagent and reliable for the oxidation of the specific double bonds. Specific double bonds, when you wanted to oxidize, then it is utilized. Yeah. So for that purpose, 5 mole percentage of osmium tetroxide is sufficient to oxidize an alkene if nano stoichiometry amount of N-methylmorpholine N oxide is used, NMO. So PM has visited today Surat and Ahmedabad, so that is why in study also it is a NMO. So this is the osmium tetroxide. These are the reaction in which it oxidizes the specific double bond. Here also in the ring it is given the double bond, so it oxidized. Now already one OH group is present, so the diol is going to form in this case. Here also it forms the diol with the around 99% when the NMO and catalyst, that is the mixture of dihydroquinone dimer, DHQ twice, and thalazine is utilized. Now here it is the osmium tetroxide is utilized for this in presence of the tosyl chloride, sodium salt of the tosyl chloride. So that gives so far the OH group. Otherwise, if this could not utilized, then it's supposed to give the diol. It's supposed to give the diol, but this is very specific reaction, so that only one OH group is remaining, and from this tosyl chloride it gives the amine. This is the bridge compound. So in bridge compound also the oxidation of the double bond is taking place in presence of the osmium tetroxide and NMO catalyst. Now here this is more steric hindrance is there, that is why this is going to oxidized. That is the less hindered double bond. Now oxidation with iodine and silver carbonate. So many of the difficulty attending the oxidation of the alkenes to the vicinal diols are taking place, but that can be avoided by using the Prevost reagent. And what is the Prevost reagent? That is the Prevost reagent, that is the solution of iodine in carbon tetrachloride that you are using uh, with the silver salt, that is the silver acetate is utilized. Silver salt is utilized for the same purpose. So that is given by the Prevost, and so that is why Prevost condition is given, and this reagent is known as the Prevost reagent. By using this, it also gives the diol via the acetate derivative, because the silver acetate is utilized in the reaction, but ultimate product gives the trans diol. This is the mechanism of the Prevost reaction. So in between I lost the network connection, that is why this thing is happening. Okay, again. So this is the basic difference between the Prevost condition. This is the Prevost condition, and this one can be considered as a Woodward condition. So this is the very specific example given, but what is the basic
सर
difference?
स्लाइड में भी दिखा दी
Huh? Oh, okay, it is
सर
all.
स्लाइड नहीं दिखाती
Okay, just hold on. Yes. So this is the Prevost condition and the Woodward condition. Prevost condition and Woodward condition. So in Prevost condition, it gives the trans product, but in the Woodward condition, it gives the cis products. That is the difference in the Woodward and Prevost condition. Now here the Prevost condition is utilized for the compound cyclohexene is there. So this can also be possible with the lead tetraacetate, but it is less selective than the pre-washed uh, reagent. So this is also good oxidizing agent, lead tetraacetate, but comparison to the pre-washed condition, this is much lower, but lead tetraacetate is also utilized as a oxidizing agent. Now Vinegar process is also there for the oxidation of the alkene. So oxidation of alkene to form the ketone is formed by the Vinegar process, in which the palladium metal is utilized in presence of the CuCl2. So this is very specific reaction where it gives the carbonyl compound. This is the another example given where the double bond is there, which gives the isomer of the compound, because the double bond is having the substituted alkene. So in that case, it can give the mixture of the isomer. Now this is good example for the oxidation of the compound having the functional group ester is given and 2 double bonds are given. So if you look at that, the ester is there and this double bond is more substituted comparison to the terminal double bond. So that is why in presence of the Vinegar process, Vinegar reagent PDCl2 and CuCl2 oxidize the terminal double bond. So this bond is going to oxidize so that this double bond will remain as it is. So in this way, this is the mechanism. In this way, the oxidation is taking place. Now another one is the selenium dioxide. This is the selenium dioxide utilized as a oxidizing reagent, but it is not that much useful. Normally selenium dioxide is utilized for the oxidation of the complex molecules or moiety that is given, but that is also oxidized because it oxidizes the other functional group also in present in the moiety. So that is why it is not selective, specific selective. So here in the previous case we had seen that the double bond was oxidized in the single ketone, but by using the selenium dioxide, it oxidized both the carbon so that it gives the dicarbonyl compound with the less yield. Here it is reported 80% yield. So here both the reagents are utilized, where the pre-washed condition, in this pre-washed condition, the iodine solution is taken in the wet salt of the silver, and here it is the iodine is taken in the dry salt of the silver. So because of that, the wet salt of the silver in presence of the iodine gives the cis diol, but whereas the another one is giving the trans diol. Now oxidation of the alkenes into carbonyl. So this is the already we had seen the Vinegar process where the alkene is converted, oxidized into the carbonyl group in the form of the aldehyde. Well, how this reaction is proceed, that's what it is mentioned. Now here it is the oxidation cleavage of the carbon-carbon double bond. So the carbon-carbon double bond is present over there, where the electronegative element is attached with any of the one carbon atom. Then how this oxidation is taking place. So just we will have the 5-minute break, and then again we will start the lecture. So uh, we will continue after 5 minutes. Okay. Oh, okay. So welcome back again. Now oxidation of the alkene by the ozone. We are using the ozone O3. So in the reaction, it is mentioned how this ozone ozonolysis is taking place. Not only that, hmm, ah, not only that, how the ozonolysis is taking place. So this is the O3, ozone is taken. So in the alkene oxidation, it forms the 5-member cyclic structure, correct? And in this setup, it disconnect or the ring is opening, and it gives the ketone and acid from the alkene. Here it is the another example. Ozone is taken in presence of the alcohol, where this intermediate step is forming. But in this case, when disubstituted alkene is there, in the previous case, it was the RCH, R dash, R double dash. Okay. Now here, in presence of the dimethyl sulfide, it gives the aldehyde and ketone. So instead of the acid, it gives the aldehyde. So that is why it is known as the controlled oxidation. Controlled oxidation. Again, the another example of the oxidation of the alkene is taken in presence of the OH group, because OH group also getting oxidized. But here the OH group remain as it is, and only the alkene group is oxidizing, and it gives the ketone. And of course, this is the another ketone that we got. So here OH group is remain unaffected. So this is the very, very important oxidizing agent, where it is not impacting the functional groups like the alcohols or esters or carbonyl group or aromatic rings present in the moiety. Now here the oxidation of the alkene, in which the moiety is having the carbonyl group. Moiety is also having the double bond in the ring, and it is also having the double bond in the side chain. So of course it is the less substituted. This double bond is less substituted. So that is why, without affecting without affecting the carbonyl group. It is going to be oxidized, but here the terminal is there, so that is why it gives the 2 moles of the aldehyde in presence of the dimethyl sulfide. So this is the application of the ozone in the different moieties. You can study later on. This is how the addition is taking place, reference to the previous slide. Now here again the ozonalized product is formed, and how this reaction is forming in presence of the dimethyl sulfide is mentioned. Now it is also a good example that the most electronegative electron withdrawing groups are mentioned. Okay, sorry, electron hello, hello.
Yes, sir.
Yeah, am I audible, Muskar?
Yes, sir.
Okay, okay. I lost the network little bit. Okay, now most electronegative elements are present, but in presence of that also ozonolysis is taking place to give the alcohol, and also in presence of the H2O2 it gives the acid, and in presence of the NaBH4 it gives the alcohol, because NaBH4, as we have mentioned, that it is utilized as a reducing agent. Now here the another reagent, that is the Lemex reagent. Lemex reagent is given. So this is consist of the dilute solution of the NaIO4, that is the oxidizing agent utilized in presence of the KMnO4 particularly. So this oxidizing agent also utilized for the formation of the diol, but not directly it forms, it also gets converted into the ketone and aldehyde. So controlled reaction is taking place. Further oxidation is not taking place, but in presence of the NaIO4 it is possible to form the uh, oxidation and get acid. Now you might have studied this in the natural product. It is in the terpenoids, this structure is coming. I forgot the name of it. But in this case, if you just look at that, this is the terminal alkene is there. Okay, not terminal, but it is disubstituted. So when oxidation is taking place of this, it is identified by formation of the ketone, particularly here acetone. So when this is oxidized as one of the fragment is generated as a acetone, and another one is generated as a aldehyde, and that is further oxidized in presence of the KMnO4, it gives the acid. So KMnO4 is very good oxidizing agent, but it directly gives the acid. Whenever we need any of the aldehyde, then it is possible to control that. Second thing, here it is also there that already aldehyde group is present in the reagent itself, and in this case it was given to double, here it was given the double bond. Okay, so this is cleavage. So here we are getting the two aldehyde group in the same moiety that is further oxidized. So this is the application of the Lemix reagent. It is also utilized in presence of the osmium tetroxide and KMNO4. This is how the KMNO4 and ozonolysis and the osmium tetroxide is taken in presence of the sodium. So here when the cyclooxidized in presence of ozonolysis is taken, then it gives the aldehyde. Gives the aldehyde. Then the taken in presence of 4, then aldehyde, but it cannot be, so immediately it oxidized into the carboxylic acid, whereas this is also possible in presence of the osmium tetroxide, that the forming. So good example discuss for the oxidation of cyclohexene. It is very difficult to oxidize the aromatic. Hello.
So there is a voice lag.
Yeah. Hello. Okay. So now we are going to discuss the oxidation of the aromatic ring. So normally oxidation of aromatic ring required harsh condition because the cleavage of the ring required the more energy. So just you can see the example that benzene when oxidized in presence of the vanadium pentoxide, it required 300 degrees Celsius temperature to get the anhydride. So this is possible, but in that case, it required higher temperature. Here naphthalene is given, that is oxidized in presence of the KMnO4. Then it is also oxidized in presence of the vanadium pentoxide. It is also oxidized in presence of the ozone. So in which, if you look at with the KMnO4 and with the ozonolysis, it gives the same product. That is the dicarboxylic acid is required. But in presence of the vanadium pentoxide, it gives the anhydride derivative. Same way, the anthracene is given. So that also oxidized in the dicarboxylic acid. So whenever ring is oxidized, naphthalene or more than two rings are oxidized, then normally it gives the dicarboxylic acid. And many of the time, if you have studied gone through the alkaloids and terpenoids and steroids, lot of oxidation reactions are discussed where the moiety of the steroids or alkaloids or terpenoids are oxidized, in which you will able to see the dicarboxylic acid formation. Now the chromic acid is also a good oxidizing agent, and quinoline is utilized in that along with the chromic acid. So it gives the complex with the pyridine 2,3 dicarboxylic acid, and now it converted into nicotinic acid by heating. One of the COH group is releasing the CO2 gas, so that we will get the nicotinic acid that tobacco is giving, and most of the time the cancer is producing due to this compound that we are consuming the cigarette or the tobacco, etc. This is the isoquinoline that also give the dicarboxylic acid in presence of the chromium tetroxide, trioxide. Probably you have not utilized so far, but in the oxidation, we are utilizing this chromium tetroxide, trioxide for the oxidation, and it gives the good result. So when this is also there in the practical, but we have not performed so far. But if you look at that, in presence of the chromium tetroxide, it gives the oxidized product where it gives the quinone. Now, dear student, that the side chain or alkyl is also oxidizing, but in presence of the chromium trioxide, it oxidizes the ring, not the side chain or any of the alkyl chain. So if you utilize the KMnO4 in place of this, then the alkyl can be oxidized. When the hydrocarbon, the anthracene is taken, it gives the anthraquinone. This is just mechanism given for your reference, how this formation of the acid is taking place in the benzaquinone via the free radical procedure. Naphthol is there. So how this diol is forming? So actually it forms the diketone, and later on it forms the diol. Now, cane is another good oxidizing agent, that is the cerium ammonium nitrate. That is also good oxidizing agent so far utilized. Then the K4-FeCN6, that is also good oxidizing agent when 2 moles of the starting material is taken, so that with the in presence of the K4-FeCN6, it gives the dimerized product, and that is the usnic acid is forming. That is known as the Fermi salt. So that Fermi salt is also utilized for the oxidation, and the phenol is oxidized in the hydroquinone in presence of the Fermi salt. Oxidation of the activated saturated CH groups, because in this case activated and non-activated both are possible. How can be activated? When any of the functional group is present in it with the ring, then activation is also there. But when it is not there and only the hydrocarbons are there, then it is considered as a unactivated. So benzylic system is the given oxidation of the benzylic system. So here, in the presence of the K2Cr2O7 or in the presence of the KMnO4, this alkyl group is oxidizing, not the ring is oxidizing. Even if the double ring was given, if it is given, then this side chain is going to oxidized in presence of the K2Cr2O7. Now, this is the activated saturated CH group where the 2 alkyl groups are attached and both are the electron donating groups. So both are oxidized and it gives the dicarboxylic acid. When single alkyl group is taken, then it oxidizes the carboxylic in the carboxylic group. But even if suppose here it is given CH2 CH3 in place of the CH3, then also it will give the only the carboxylic group, single carboxylic group. So whether it can be given methyl or ethyl or propyl, but oxidized product can be the benzoic acid. So this can be carried out by the Attard reaction. So first it is oxidized in the aldehyde and then immediately it is converted into oxidation carboxylic group. So this is the controlled reaction where 2 methyl groups are given, but in presence of the chromium trioxide and by using the acetic anhydride, the selective oxidation is taking place. So only one of the group is oxidized. Thus, another one is the CrO2Cl2 is utilized for the oxidation, and that also gives the oxidized product, that is the aldehyde. Can, as we have discussed, that is oxidized in presence of the many substituent here. So that is why this is the specific application of the can, where any one of the alkyl group is oxidized in the aldehyde group and later it is oxidized in the another one. But in presence of that, if you utilize the Cr2O7 or KMnO4, then all the alkyl groups are going to oxidized. But the can is the having the specificity so that it oxidized only the specific alkyl group. Selenium dioxide at higher temperature, it is also oxidized. It is also oxidized, but in the ketone. but it required around 300 to 500 degrees Celsius temperature in the complex moieties. Lead tetraacetate, as we have mentioned, that is also utilized for the oxidation. So this is the another type of moiety when allylic position, allylic moieties are given. So in this case, if you look at, this is the carbon-carbon double bond. So next carbon is known as the allylic carbon. So this carbon is the allylic carbon. So carbon having the functional group attached, that carbon is the allylic carbon. So this allylic carbon is oxidized, okay, in presence of the double bond. So in presence of the SeO2. So double bond remain as it is not oxidized, only the allylic carbon is oxidized. That is the specificity of the selenium dioxide. Here the different allylic carbons are taken, okay. Here it is the double bond, here it is the double bond, and here it is the double bond. All these are the allylic carbon, okay. But in that case, you need to remember the reactivity of this CH2 is more reactive than CH3 and then CH, okay. So in that case, here CH2 group is going to oxidize. That is why we are getting the alcohol. Now for this case, both the CH3 groups are there. So any one of the CH3 group is oxidized. But for this condition, here it is the CH3 and here it is the CH2. So CH2 is going to oxidized this. So that is why this carbon is oxidized. These are the another application in the application of the selenium dioxides are given, where the sigmatropic rearrangements are different sigmatropic rearrangements are taking place. How the formation is taking place in the 2,3 sigmatropic rearrangement by using the selenium dioxide. Now this is the one more oxidizing agent, that is the NBS, N-bromosuccinimide. So again, in the presence of the double bond, it is oxidized, okay. Now you can see that it is also oxidized in the definition based on addition of the electronegative group. So here it is the electronegative group. So this is the green method for the bromination, N-bromosuccinimide. But along with that, we are getting the oxidizing product. But this is more utilized for the bromination, alternative of the Br2 water. Now this is the another application that NBS is utilized in presence of the AIBN. This question was asked in the NET examination, AIBN, utilization of the AIBN. So oxidation is always taking place at the allylic carbon. So this is the allylic carbon where bromination is taking place. And if you further oxidize, then you will get the oxidized product. But as I have mentioned, that NBS is more useful for the bromination. And when the Hoffman product is given, or when the double bond is at the end of the alkene, terminal alkene is there, then it is possible to get the mixture of the brominated product. So this is how the bromination is taking place. Now this is the very recently PCC is utilized as an oxidizing agent, and this is also very specific oxidizing agent, where in presence of the any of the functional groups that can be protected if it is more reactive. but in presence of the double bond, the allylic carbon is oxidized. That is the application of the PCC. Mercury acetate is also utilized as a oxidizing agent, where it is also oxidize the allylic carbon atom. This is the allylic carbon atom. This is also allylic carbon atom, but it is having the more hindrance due to the presence of the alkyl chain here. So that is why it is more easy to oxidize the allylic carbon. So same thing here, it is the oxidized the allylic carbon atom in presence of the lead tetraacetate and the mercury tetraacetate. Now this is the system where CH2CO, okay, here it is the CH2CO system is there, that is also oxidized. Here also you can say CH2CO, it is a CH2 and here it is the CO. So it is oxidized in the presence of the selenium dioxide. This is also, you can consider the CH2CO system. This is the CH2, so that diketone is forming. Now this is very interesting example where already ketonic group is given and selenium dioxide is given. So in that case, either of the ketone, either of the carbon is oxidized, but when diketone is given and oxidation is carried out, then the sandwich CH2 group is sandwiched by the two ketonic group, and that is why this CH2 group is going to oxidized. In the same way, this is also sandwiched by the diketone, so that is why this CH2 is going to oxidize and forming the ketone. Now alkyl nitrile is there, so that is also good oxidizing agent for the formation of the oxidation of the CH2 group in presence of the ketonic group. Now this is the very good oxidizing modern oxidizing agent, that is the KHMDS. So this is the oxidizing agent. Recently it is utilized in the industry, so that also utilized in the oxidation where particular alcohol is forming next to the carbonyl carbon atom. Say this, here the OH is forming. In this case, if you look at, this is the carbonyl group, okay, so next is the CH2, so here the alcohol is going to form in the presence of the KHMDS. This is the structure of KHMDS. Now this is the unactivated CH group, because this is the purely hydrocarbon and it is required to oxidize this carbon atom, because it is having the zero level oxidation state. So KMnO4 is possible to oxidized because only one H is there, so OH group is forming. So this is the unactivated CH group example. Barton reaction is very famous reaction where the oxidation, this is the NO2 group, okay, here it is the NO2 group. So oxidation is taking place at alpha, beta and gamma position. This is the photolysis photochemistry reaction Barton that you have studied in the semester 2 in the photochemistry, okay. So where the ketonic group is forming here, and at this it is the forming the OH. It goes through the free radical mechanism. This is the natural product is taken, where in the same case OH is there, where oxidation is taking place. Hoffman-Lofter-Freytag reaction, where the N-haloamines are giving, where delta carbon is oxidized. This is the GIF chemistry, and that mechanism is given. Oxidation of amine. So as we have mentioned that oxidation of amine gives the NO2. Okay. So this NH2 is oxidized in the NO2. Reduction is NH2 and oxidation is NO2. This is the NH2. So it is NO2, NH2 it is given. So here it is the in presence of the MnO2, it gives the diketone, but in the presence of the ammonium disulfate, it gives the NO2 and the per acid of the fluorine. The imine is there, that is also primary, secondary, and primary amine if taken. So that is also oxidized in the presence of the H2O2, and hydroxyl amine is obtaining. Here oxime, finally it gets converted, hydroxylamine is converting into the oxime. So this is the same thing, it is NO2, NH2 is oxidized into the NO2. Okay, so it is the primary amine, NH2, secondary amine gives the hydroxyl amine, and finally it is oxidized into the oxime. Tertiary amine is not giving any oxidized product, but in the presence of the previous in the per acids, but it is giving in presence of the H2O2. Tertiary amine, where N oxides are obtaining. We had seen some of the examples of N oxide in the semester 1 in the unit 1 in 402. When hydrazine is given, hydrazine NHNH2, it oxidized in the hydrocarbon. So NHNH2 was there, it is oxidized in the hydrocarbons. Then if sulfides are given, okay, sulfides are given, so it is oxidized in the sulfoxides in the presence of the per acids, and further oxidation gives the sulfones, correct? So this is also possible by taking the KMnO4 directly. Sulfone is also possible. So all these oxidizing agents are discussed for the particular reference, particular functional groups. You can go for the detailed study about the different functional groups and the oxidizing agents to get more about it. I have just thrown the light on the oxidation of the functional groups in the limited period of time. So with that, I am completing this oxidation of the functional groups. I have taken this very fast and I have not discussed detailed chemistry due to the time constraint, but just I have gone through the set of the reactions so that you will get an idea. I have shared the PPT. You can refer any of the reference books, and a lot of reactions are given over there. So finally, I am concluding this lecture here, and we will meet in the another lecture. So thank you for attending this lecture. Before you leave, this class, just speak out your roll number so that I can note down. Just you can speak out your roll numbers. GIA 62. Okay.
GIA 32.
32.
GIA 44.
HPP 64.
Just a minute. GIA 40.
4.
44. Okay, next.
HPP 64.
64. HPP or
GIA
GIA?
6.
HPP.
HPP. Okay. GIA, anybody left?
GIA 6.
6. Okay, Prajapati. GIA 6. Okay.
GIA 63.
GIA 63. Okay.
GIA 28.
28. GIA 28. Rocky. Yes. Anybody left? Okay, fine. So thank you. Thank you so much. Okay. Now you can leave the meeting.